So as our final example of a user-defined data structure, we will look at binary search trees. So we are looking at a situation where we need to maintain dynamic data in a sorted manner. Remember that one of the byproducts of sorting is that we can use binary search to efficiently search for a value. But binary search can be used if we can sort the data once and for all and keep it in sorted order. If the data is changing dynamically, then in order to exploit binary search, we'll have to keep resorting the data, which is not efficient. So supposing we have a sequence of items and items are periodically being inserted and deleted. Now, as we saw with heaps, for instance, if we try to maintain a sorted list and then keep track of inserts, then each insert or delete in this case would take order n time, and that would also be expensive. However, it turns out that we can move to a tree-like structure or a tree structure like in a priority queue, we move to a heap and then do insert and delete also efficiently alongside searching. So the data structure we have in mind is called a binary search tree. So in a binary search tree, we keep exactly one copy of every value. So it's like a set. We don't keep duplicates. And the values are organized as follows. For every node, all values which are smaller than the current node's value are to the left, and all values that are bigger than the current node value are to the right. So here is an example of a binary search tree. So you can check, for instance, that to the left of the root 5, we have all values 1, 2 and 4 which are smaller than 5. And to the right of 5, we have the values 8 and 9 which are bigger. Now this is a recursive property. So if you go down, for instance, if you look at the node labeled 2, then below it, it has values 1 and 4. Since 1 is smaller than 2, 1 is to the left of 2. And since 4 is bigger than 2, 4 is to the right of 2. Similarly, if you look at the node 8, it has only one value below it, namely 9. And therefore, it has no left child, but 9 is in the right subtree of 8. So we can maintain a binary search tree using nodes exactly like we did for our user-defined lists, except in a list we had a value and a next pointer. In a binary search tree, we have two values below each node potentially, a left child and a right child. So each node now consists of three items, the value being stored, the left child and the right child. So if we look at the same example that we had before on the right, then the root node 5 will have a pointer to the nodes with 2 and 8. The node 2 will have a pointer to the nodes 1 and 4. These are now what are called leaf nodes. So they have no children. So their left and right pointers will be none, indicating there is nothing in that direction. Similarly, 8 has got none as its left pointer because it has no left child, and the right pointer points to 9. And the node with 9 again has two none pointers because it's a leaf node. Now it will turn out that we will want to expand this representation in order to exploit it better for recursive presentations. So what we will do is that we will not just terminate the tree with a value and two pointers none. We will actually add a layer of empty nodes with all fields none. With this, the empty tree will be a single empty node. And a leaf node that is not none will have a value and both its children will be empty nodes. So it won't directly have none as its left and right pointers. It will actually have children which are empty. So this makes it easier to write recursive functions. And if we don't do this, then it's a bit harder to directly implement recursive functions. So just to understand how our tree structure changes, this is the structure that we had before, the same example. Okay, so here notice that in the leaf nodes, okay, the leaf nodes have a value and both the child pointers left and right are directly none. So we want to change this. What we want to do is we want to insert below this an empty node. At everywhere where we see a none, we want to insert an extra empty node. So this of course blows up the tree a little bit, but then this cost is not that much as you can calculate. So if we do this, then we get a new tree which looks like this, right? So below every leaf node, wherever we normally had a none pointer indicating that the path has ended, we will explicitly add one extra node which has all three fields none. And it will turn out that this is very useful to clean up our programming later on. So this is the representation that we'll use for a binary search tree. Each node has 3 pointers, and at the leaves we have an extra layer of empty nodes with all three values none, none, none. So here is the basic class tree. So as before, we have an init function which takes an initial value which is by default none. So the init function works as follows. Okay? So we first set up the value to be the init val, which could be none. If there is a value, then we create a tree with one node, in which case we have to create these empty nodes. So notice that if we go back and we don't give a value, so maybe it's better to look at this case. Okay? If we don't give a value, then we end up with a tree which just says none, none, none. So this is our empty tree. So the initial value is none, we get this tree. If the initial value is not none, then we get a tree in which we put the value v, and then we make the left and the right pointers both point to this none, none. So this is a tree that will contain exactly one value. So depending on whether init value is none or not none, we end up either a tree with 3 nodes with 2 dummy nodes below, or a single empty node denoting the empty tree. So given this, as before, we have the function isEmpty, which basically checks if the value is none. So if I start looking at the tree and the very first node says none, then that tree is empty, otherwise it's not empty. So let us first look at a way to systematically explore the values in a tree. So these are called traversals, and one traversal which is very useful for a binary search tree is an in-order traversal. So what an in-order traversal does is that it first explores the left side. So it will first explore this recursively, again using an in-order traversal. Then it will display this, and then it will explore the right. Okay, so if you see the code, you can see that if the tree is not empty, you first do an in-order traversal of the left subtree, then you pick up the value at the current node, and then you do an in-order traversal of the right subtree, and this produces a list of values. So if we execute this step by step, so 5, if we reach, it says first do an in-order traversal of the left, so we come down to 2. This is again not a trivial tree, so again we have to do an in-order traversal, so we go to its left. And now when we have 1, an in-order traversal of 1 consists of its left child, which is empty, 1, and then its right child is empty, so this produces 1. Now I come back and I list out the node 2, and now I do an in-order traversal of its right. So I've got 1, 2, 4. So this completes the in-order traversal of the left subtree of 5. Now I list out 5 itself, and then I do an in-order traversal of 8 and 9. Since 8 has no left child, the next value that comes out is 8 itself, and then 9. So what you can see is that since we print out the values on the left child before the current value and the values of the right child after the current value, with respect to the current value, all these values are sorted because that's how a search tree is organized. And since this is recursively done at every level down, the final output of an in-order traversal of a search tree is always a sorted list. So this is one way to ensure that the tree that you have constructed is sorted. You do an in-order traversal, that the tree you have constructed is a search tree. You do an in-order traversal and ensure that the output that you get from this traversal is a sorted list. So as we mentioned at the beginning of this lecture, one of the main reasons to construct a search tree is to be able to do something like binary search. And this is with dynamic data, so we will also have insert and delete as operations, but the main fundamental operation is find. So like in binary search, we start at the root. So imagine that this is the middle of a list or an array, for example. We look at this element. If we have found it, it's fine. If we have not found it, then we need to look in the appropriate subtree. Since a search tree is organized with the left value smaller and the right value is bigger, we go left if the value we are searching for is smaller than the current node, and we go right if it is larger than the current node. So this is very much a generalization of binary search in the tree. So here is the code. It's very straightforward. We want to find a value v, and remember this is this Python syntax, so we always have self as the first parameter to our function. So if the current node is empty, we can't find it, so we return false. If we do find v, then we return true, and if we don't find v, then if it is so this is not t, it should be self. If it is smaller than this current value, then we go left and search for it. Otherwise, we go right and search for it. Okay? So this is exactly binary search, and it's a very simple recursive thing which exactly follows the structure of a search tree. It will be useful later on to be able to find the smallest and largest values in a search tree. So notice that as we keep going left, we go smaller and smaller. So where is the minimum value in a tree? It is along the smaller leftmost path. So if I have to go down the leftmost path, and if I can't go any further, then I find it. So we will always apply this function only when the tree is non-empty. So let's assume that we are looking for the minimum value in a non-empty tree. Well, we find the leftmost path. So if I cannot go further left, then I have found it. So in this case, if I reach 1, since I can't go further left, 1 is the minimum value. Otherwise, if I can go left, then I will go one more step. So if we start this, for instance, at 5, it will say that 5 has a left subtree. So the minimum value below 5 is the minimum value below its left child. So we go to 3. Now we say that the minimum value below 3 is the minimum value below its left child. So we go to 1. Then we say that the minimum value is the minimum value at 1 because there is no left child, and therefore we get the answer 1. And it is indeed true that anything below that is only on the right, and that is 2. So dually one can find the maximum value by following the rightmost path, right? So if the right is none, then we return the current value. Otherwise, we recursively look for the maximum value to our right. So in this case, we start at 5, we go down to 7, then we go down to 9. And since there is no further right path from 9, 9 must be the maximum value in this tree. We will come back later on and see why we need this minimum and maximum value. But anyway, it's a useful thing to be able to find. And it's very easy to do so, again, using the structure of the binary search. So one of the things we said is that we need to be able to dynamically add and remove elements from the tree. So the first function that we look for is insert. So how do we insert an element in the tree? Well, it's quite easy. We look for it. If we don't find it, then the place where our search concludes is exactly where it should have been. So we insert it at that point. Right? So for example, supposing we try to insert 21 in this tree. Well, we look at 52 and we go left. Then we go left. Then we come to 16 again and we go right. Then we come to 28 and we find that we have exhausted this path and there is no possible 21 in this tree. But had we found 21, it should be to the left of 28, so we insert it there. So we look for where we should find it, and if we don't find it, we insert it in the appropriate place. Similarly, we can start and look for 65. So 65 is bigger than 52, so we go right. Then it's smaller than 74, so we go left. But there's nothing to the left of 74, so we put it to the left of 74. Now insert will not put in a value that is already there because we have no duplicate. So if now we try to, for instance, insert 91, then we go right from 52, we go right from 74, and now we find that 91 is already present in the tree. So insert 91 has no effect on this tree. So this is a very simple modification of the find algorithm. So we keep searching, and if we reach the leaf node, then we come to an empty node, right? So if we find that we have reached an empty node, then we do the equivalent of creating a new node here. We set this value to be V, and we create a new frontier below by adding 2 empty nodes on the left and right rather than just having none. On the other hand, if we find the value in the tree, we do nothing. And if we don't find the value, then we just use the search tree property and try to insert either on the left or on the right as appropriate. How about delete? So delete is a little bit more complicated than insert. So basically, whenever we find V in the tree, and there can only be one V, remember, this is not like deleting from the list that we had before where we were removing the first copy of V. In a search tree, we have only one copy of every value, if at all. So if we find V, we must delete it. So we search for V as usual. Now, if the node that we are searching for is a leaf, then we are done. We just delete it and nothing happens. If it has only one child, then we can promote that child. If it has 2 children, we have a hole. We have a leaf, we have a node which we have to remove value, but we have values on both sides below it. And now we will use this maximum function, maxval or minval, in order to do the work. So let us just see how this works through some examples. Right? So supposing we first delete 65, then we first search for 65, we find it. Since it is a leaf, okay, then we are in this case, the first case, we just have to remove this leaf and we are done. Now we try to delete 74. So we find 74 and we find that it has only one child. So if it has only one child and we move this out, then we can just effectively short circuit this link and move this whole thing up and make 52 point to 91 directly. So we are in this second case. This is what it means to promote the child. So the deleted node has only one child. we can bypass the child and directly connect the parent of the deleted node to the one child of the deleted node. So this will result in 91 moving up there. Now finally, we have the difficult case, which is we want to delete a node which is in the middle of the tree, in this case 37. So we come to 37 and we want to remove this. Now if we remove this, there will be a vacancy. Now what do we fill the vacancy in, and how do we adjust the shape of the tree? So we look to the left and find the maximum value. Remember that everything to the left is smaller than 37 and everything to the right is bigger than 37. So among the left nodes, we take the biggest one and move it there. Then everything to the left will remain smaller than that node. We could also do it the other way and take the smallest value from the right, but we won't do that. We will stick to taking the maximum value from the left. So we go to the left and find the maximum value is 28. So basically we have taken this 28 and moved it up there. Now we should not have two copies of 28, so we need to remove this 28. So how do we do that? Well, within this subtree, we delete 28. Now this looks like a problem because in order to delete a node, we are again deleting a node. But remember that the way that the maximum value was defined, it is along the rightmost path. So the rightmost path will either end in a leaf or it will end in a node like this, which has only one child. And we know that when we have a leaf or only one child, we are in the first two cases which we can handle without doing this maximum value delete. So we can just walk down, remove the 28 and promote the 21. Okay, so this is exactly how delete works. So we can now look at the function. So if there is no value v, then we just return. The easy cases are when we don't find v at the current thing. So if it is less than the current value, then we go to the left and delete. If it is bigger than the current value, we go to the right and delete. So the hard work comes when we actually find v at the current value. So if this is a leaf, now we haven't shown how to write this function, but if this is a leaf, this means that it has left and right child both as empty nodes. If this is a leaf, then we will make it empty. We will see how we do this in a minute. I'll just show you the code for this. So if this is a leaf, we delete it, right? This is the first case, the simple case. If this is a leaf, we just delete it and we make this node empty. If on the other hand, it has only one child, okay, so actually in this case, if the left is empty, then we just promote the right, okay, and if its left is not empty, then we will copy the maximum value from the left and delete the maximum value on the left. So we need to just see these two functions here, make empty and copy right. So make empty just says convert this into an empty node. An empty node is one which all three fields are none. So we'll just say self.value is none, self.left is none, self.right is none. So if it had an empty node hanging off it, those empty nodes are now disconnected from the tree. Okay, so this is this make empty function. And now the copy right function just takes everything from the right and moves it up. So it takes the right value and makes it the current value, the left value, right dot left and makes it the left. So we just take basically this node and copy these values one by one here. So we copy right dot value to the current value, right dot left to the current left, right dot right to the current right. So how much time do all these take? Well, if you examine the thing carefully, you would realize that in every case, we are just walking down one path, searching for the value. And along that path, either we find it or we go down to the end and then we stop. So the complexity of every operation is actually determined by the height of the tree. If we have a balanced tree is one where you can define that each time we come to a node, the left and the right child roughly have the same size. If we have a balanced tree, then it's not difficult to see that we have height, logarithmic in it. This is like a heap. A heap is an example of a balanced tree. A search tree will not be as nicely structured as a heap because we will have some holes, but we will have logarithmic height in general. We will not explain how to balance a tree in this particular course. You can look it up. You can look for a topic called AVL trees, which is one variety of balanced trees which are balanced by rotating subtrees. So it is possible while doing insert and delete to maintain balance at every node and ensure that all these operations are logarithmic. So let's just look at the code directly and execute it and convince ourselves that all the things that we wrote here actually work as intended. So here we have a Python code for the class tree that we showed in the lectures. So we have just added a comment about how the empty node is organized and the leaves are organized. So there is the constructor which sets up either an empty node or a leaf node with two empty children. Then we have is empty and is leaf, which check whether the current value is none or both the left and right children are empty respectively. Then we have this function make empty, which converts the leaf to an empty node. Copy right copies the right child values to the current node. And then we have the basic recursive functions. So we start with find. Okay? So find is the one which is equivalent to binary search. Then insert is like find, and then where it does not find, it tries to insert. And finally, we have max val, which we need for delete. And delete now, when we reach the situation where we have found a value that needs to be deleted, if it is the leaf, then we remove the leaf and make it empty. If it is the left child is empty, then we copy the right child up. Otherwise, we delete the maximum from the left and promote that maximum value to the current. Finally, we have this in-order traversal, which generates a sorted list from the tree values, and the str function just displays the in-order traversal. So now if we load this, then we can, for instance, import this package, set up an empty tree, and then put in some random values. It's important not to put it in sorted order, otherwise a sorted tree, if we just insert one at a time, it will just generate one long path. Okay, so I'm just trying to put it in some random order. So we insert into the tree all these values. And now if I print T, it will give me a sorted version of this. So 1, 2, 3, 4. So I can now insert more values. So I can, for example, insert 17 and verify that now 17 is there between 14 and 18. And I can keep doing this. I can even insert values in between, like 4.5, because I've not specified the integers, right? So it puts it between 4 and 5 and so on. And now I can delete, for example, if I delete 3, then I find that I have 1, 2, 4. If I delete, for example, 14, then I no longer have 14 between 7 and 17 and so on. Right? So this implementation definitely works, although we haven't balanced it. So if we don't balance it, then the danger is that if we keep inserting in sorted sequence, so if we keep inserting larger values, it keeps adding on the right child. So the tree actually looks like a long path. Right? So then it becomes like a sorted list, and every insert will take order n time. But if we do have rotations built in, as we could using an AVL tree, then we can ensure that the tree never grows to height more than log n. So all the operations insert, find, and delete will always be logarithmic with respect to the number of values currently being maintained.